We've all heard the phrase Bermuda Triangle, a foggy, sensational label for a patch of ocean where ships and planes once vanished from headlines. But up above Earth, there's a different kind of mystery people like to call the Space Bermuda Triangle, a narrow equatorial orbital region where spacecraft teams have reported blackouts, anomalies, and occasional mission-ending events. Today we'll ask a careful question. What is actually happening up there? Are satellites really vanishing for mysterious reasons? Or are there well-understood space physics and engineering explanations? First, let's locate the hotspot we're talking about. The most commonly discussed near-Earth problem zone lies over the South Atlantic and parts of South America and West Africa. Scientists call one key feature in this area the South Atlantic Anomaly, a region where Earth's inner Van Allen radiation belt dips particularly close to the planet, so energetic charged particles are much more abundant than elsewhere at those altitudes. Satellites passing through experience higher fluxes of energetic particles that can disturb electronics and cause single-event upsets in memory or sensors. This isn't science fiction, it's a mapped, measured phenomenon that mission planners account for when designing orbits and shielding. But the SAA alone doesn't explain every anomaly. Another major class of events involves ionospheric disturbances, regions in the upper atmosphere that suddenly ionize or develop irregularities and screech GPS and radio signals. A particularly instructive case comes from ESA's Swarm mission. Operators noticed GPS blackouts at night over the equatorial band between South America and Africa. After investigation, scientists traced these blackouts not to aliens but to intense ionospheric storms or localized plasma irregularities, often triggered by solar radiation and atmospheric dynamics. Understanding those processes required correlating magnetic field measurements, GPS signal drops, and ionospheric monitoring. This is a good example of careful scientific detective work replacing mystery with mechanism. Space weather, the sun's temper, is another major player. Coronal mass ejections and high-energy particle events can disrupt spacecraft electronics, degrade solar panels, and even cause sudden increases in atmospheric density at low Earth altitudes. In extreme cases, geomagnetic storms heat and inflate the upper atmosphere, increasing atmospheric drag on low-orbit satellites and hastening orbital decay. There have been documented episodes in which intense geomagnetic activity coincided with large numbers of satellite anomalies and even re-entries. These are not conspiracies, they're predictable physical effects of a variable star. We should also be clear about practical engineering causes. Satellite hardware and software are complex. Single-event upsets from high-energy particles can flip a memory bit. Onboard software can mishandle an unexpected telemetry spike, and attitude control thrusters can fail. Sometimes those low-level faults cascade into a loss of control. Mission failure reviews often show that a combination of factors, a radiation hit at a critical moment, degraded components, or an operator command error during a high-risk maneuver, is the culprit. In many historical cases, the underlying cause is entirely terrestrial and technical. That said, there are real patterns that deserve investigation. The equatorial band we discussed is simultaneously a region where the magnetic shielding is weaker, SAA, where ionospheric irregularities are common, particularly at night and during certain seasons, and where charged particle precipitation is enhanced, so multiple stressors line up. When a satellite traverses that band, engineers see a higher than baseline rate of upsets and transient blackouts. That clustering of anomalies is exactly why researchers have called it a problem zone, and why agencies obsessively monitor it. But clustering is not the same as mystery. It's a pattern that can be studied and mitigated. Now a natural follow-up, what about claims that entire satellites vanish without a trace? The idea conjures images of advanced technology plucking our hardware from orbit, but what's really going on? In public conversation, such claims sometimes refer to satellites that suddenly stop transmitting, effectively going dark. Or they might refer to satellites that re-enter uncontrolled and burn up, looking like a sudden fiery disappearance. But careful analysis often finds plausible explanations. Unmitigated orbital decay from enhanced atmospheric drag, collision with debris, even a tiny fleck can be catastrophic. Propulsion or power system failures, or events triggered by solar storms. In some historical instances, initial public reports overstated the drama, fueled by the 24-hour news cycle. Later, once all the data is analyzed, detailed technical reviews clarified the mundane chain of failures. Another wrinkle adds to the mystery: certain military or national security satellites are highly classified. When these experience anomalies, the details are not disclosed to the public. That secrecy creates an information vacuum that can feed speculation. However, secrecy and classification are policy facts, not evidence of extraterrestrial interference. An information gap driven by national security is not proof of alien activity. What about the idea of mysterious magnetic fields that actively steal satellites? Earth's magnetic field is complex and changing. It has dense, lobes, and slowly drifting features driven by dynamics in the planet's core. The SAA is one such irregularity. But magnetic fields alone don't grab satellites. They influence charged particles and radiation environments that, in turn, affect electronics and plasma conditions. The physical chain is core dynamics, magnetic field geometry, radiation belt shape, and particle flux, increased chance of electronic upset. The chain is measurable and modelable. It doesn't require anomalous forces or unknown physics. Another important mechanism to highlight, and one that surprised many when the evidence accumulated, is how solar-driven upper atmosphere heating can increase atmospheric density at satellite altitudes during solar maxima. That extra drag shortens lifetimes and can even cause rapid re-entry of large numbers of satellites, especially poorly tracked or low-mass objects. In 2022, a major space weather event accelerated re-entry in some satellites and contributed to a significant increase in loss events for certain constellations. This is a reminder that natural space weather can have systemic effects on large populations of spacecraft. We should also survey what the scientific community has done to study these phenomena. Multi-satellite missions like ESA's Swarm and NASA NOAA space weather monitoring fleets have been essential. They combine magnetometers, particle detectors, and GPS receivers, allowing researchers to correlate magnetic irregularities, particle flux, and signal blackouts. Advances in modeling, from magnetospheric models to coupled atmosphere-ionosphere simulations, have turned puzzling observations into predictive capability. In other words, the more we instrument the region, the less mysterious it becomes. Let's address the elephant in the room: alien or deliberate interference. When a culturally resonant mystery like the Bermuda Triangle is mapped into space, sensational narratives proliferate. Responsible science requires extraordinary evidence for extraordinary claims. To date, there is no peer-reviewed evidence published that supports non-natural interference with satellites in these regions. The anomalies that are best documented are consistently explainable, at least in part, by known space physics, engineering failures, or data gaps. That does not mean we know everything. It means the burden of proof lies with anyone making claims of unknown agents, and so far that burden has not been met. If you see an authoritative paper claiming otherwise, scrutinize methods and reproducibility. What about the persistent stories of hidden data or secret analyses by government agencies? It's a compelling idea and not entirely without basis. It's true that some military and intelligence programs are classified for national security reasons, protecting sensitive technologies or operations. Consequently, not every anomaly they encounter is published openly. Even for declassified incidents, the public record can be incomplete. Technical failure review boards often publish redacted reports. These blacked-out sections aren't necessarily hiding a conspiracy. They typically protect sensitive personnel data, proprietary engineering details, or information that could compromise other, still classified systems. But this secrecy isn't the whole story. For civilian science archives, from NASA, ESA, and academic groups, the trend has been a powerful move toward radical transparency. Vast public datasets from missions like the Hubble Space Telescope or Mars rovers are available to anyone with an internet connection. This culture of openness is precisely how the Swarm satellite blackout puzzle was solved. The solution wasn't found in a secret file. It was pieced together publicly by international teams sharing measurements and analysis across different scientific disciplines. So, if you're investigating an anomaly, where should you look? Official mission reports and peer-reviewed technical papers are primary sources. For U.S. agencies, Freedom of Information Act channels provide a formal route for requests. But expect that truly classified programs will remain opaque because secrecy is their fundamental design. So what does this mean for satellite operators and for the public? First, redundancy and hardened design matter. Radiation-hardened electronics, error-correcting memory, and safe mode behaviors dramatically reduce mission risk. Second, better space weather forecasting and more in-situ observations reduce surprise. Third, better tracking of debris and more careful end-of-life planning reduce collision and uncontrolled re-entry risks. Finally, Robust transparency and careful communication by agencies help separate sensational rumor from real operational risk. So to wrap this all up, yes, there is a genuine problem zone in low Earth orbit where anomalies cluster. This isn't a mystery, it's a known environmental hazard. The culprit is the South Atlantic Anomaly, a dip in our planet's magnetic field that allows high-energy particles to get dangerously close. Engineers treat this with extreme seriousness because ignoring it means risking multi-million-dollar assets and critical data. But the data-driven story is one of proactive science and methodical engineering, not of mysterious forces snatching satellites. For every glitch, there are thousands of successful passes, achieved through careful planning, robust shielding, and software designed to handle radiation hits. It's a constant, calculated dance with a known risk. If you want to follow the real ongoing science, the data is public. Look at the European Space Agency's SWARM mission, which is mapping the magnetic field with incredible precision. Dive into NASA's extensive work on the SAA and the space weather analyses from agencies like NOAA. These are the front lines where speculation is replaced by measurement and where mystery is systematically turned into a predictable mechanism. If this kind of deep dive grabbed you and you value evidence over speculation, consider subscribing. We're dedicated to unpacking the real data behind the universe's greatest questions, from the quirks of our own planet to the mysteries of distant galaxies. We'll continue to bring you insights from the scientists and engineers on the front lines, helping you separate the genuine risks and wonders of space from the persistent myths.